So I'll go ahead and get started. So today we'll be focusing on TI 60 gigahertz AWR 6843 AOP, particularly discussing some in-cabin sensing solutions. But some background, this AWR 6843 AOP is part of the mmWave sensor category of devices at TI. For those unfamiliar, mmWave sensor is a type of radar sensing that provides range, velocity, and angle information. Typically, it works in environments that can be challenging for optical or other types of solutions, including poor lighting condition, rain, snow, and extreme temperatures. This is one of the advantages of using a radar-based technology instead. Specifically, the mmWave sensor that we're working on is a single chip, low power sensing solution using RF CMOS technology. We have integrated both the antenna on the package as having scalable software and various different devices. With the antenna on package, you get a smaller form factor as well as simplifying your R&D and development process. Typically with several cascaded radar front ends, you can also achieve a LiDAR-like performance on the point for the point cloud at a significantly cheaper cost. Applications of mmWave sensors include both automotive and industrial applications. We'll mainly be talking about in-cabin sensing today, but I do want you to keep in mind that radar technology is fundamentally good at both detecting motion and localizing it. And that's why we'll discuss for an in-cabin application how we use this ability to detect very fine motion and localize it for several different applications of in-cabin sensing. But this could also be extended to more consumer type applications such as gesture monitoring, vital signs, heart rate detection, things like that. It's all the same kind of technology. TI provides various demo software that can be used to assess any of these kinds of capabilities. But the use case we'll deep dive into today is focused on in-cabin sensing. So why we care about mmWave sensors for occupancy detection? We've seen a lot of market trends where there's a requirement to be able to detect an unattended child in a vehicle, be able to detect and localize in a typical cabin how many people are in the car and at which seats they're sitting in for more accurate seatbelt reminder systems. You may have experienced in your everyday life typical issues where a gym bag left on a seat or something like that will trigger a safety seatbelt reminder, which tends to be ignored or annoying. One of the capabilities of radar is to be able to detect specifically if it's a living or a human being in the seat, and be able to give a more advanced kind of sensing response. So what we've seen is that a single radar sensor can be able to displace typically the weight sensors that are used in vehicles. This has a cost benefit as well as an easier integration for frame manufacturers, as a single sensor now replaces multiple sensors that have to be embedded in the seats. For the same reason, using these seatbelt or seat occupancy detection, it can also be used for airbag control and other occupant monitoring functions, such as direction of airflow and things like that, for more smarter response within a vehicle. Compared to other kinds of sensors, these active mmWave sensing gives us both higher accuracy in detecting the kind of occupancy that is specific to humans, and then also being able to localize them within the cabin to know is it the back seat or the front seat where the human is. Generally, also there's an ability to also start looking at whether it's an adult or a child that's been in the car, and give us that kind of distinction that typically other sensors that have been used for motion sensing haven't been able to have that kind of intelligence. Okay, so an overview of the radar portfolio, the 60 gigahertz radar portfolio. So when we talk about radar, there's two different frequency bands that TI offers devices in 60 gigahertz and the 77 gigahertz device. Generally, the devices are pin-to-pin compatible for their equivalent counterpart in frequency. So, for example, the 1843 and the 6843 are similar in functionality. The main difference is that baseband, that center frequency that they operate at. So the 60 gigahertz devices will go from 60 to 64 gigahertz. 77 will go from 77 to 81, having 4 gigahertz bandwidth. The main thing is the frequency that is suitable for the application and the regulations that it apply across different regions of the world would determine the selection of one device versus the other. So if we look at the top end of our portfolio, this is both the 6843 and the 1843 devices. They feature a DSP as well as 1.75 megabytes of memory. This allows you to run all the demos that we provide entirely on the device and providing an edge sensing solution. The advantage of this also, though, is that when we scale down from a 6843 to a 6443 type device, the main difference is the reduction in memory, and then the 6443 device have the DSP. However, a lot of the software investments that are made on one platform can be scaled to the other platform. For example, devices that don't use the DSP for additional processing like classification and things like that could be run instead on the 6443 for cost optimizations. Additionally, there's a 2243 device in the 77 gigahertz family that is just the front end, allowing all the processing to be done on the host processor. For automotive applications, there's also the ASIL B safety target. There's for every device here you see, there's excepting the AWR 2243 right now, there is an industrial variant where the main difference is the temperatures in which they operate at, as well as other safety related differences. However, if your application doesn't require automotive safety capabilities, those might be more suitable. But generally, the same demo software that we see would work on either any of the AWR or IWR device the equivalents. So if we get into vehicle occupancy detection, we see this example here where the radar is mounted up at the front in the same perspective as the camera image here. This radar here is front mounted using our antenna on package device and has a wide field of view, actually wider than what you can see in the camera itself, about plus or minus 60 degrees. And so we can see that a child here, this is what we refer to as our heat map based detection. So at the more low level detection, before typically radar provides point cloud information, but you can also choose to build algorithms based off of the heat map that's produced from radar data. And I say heat map in terms of energy, reflected energy intensities, and not actually temperature. But here we can see that the presence of the child causes this hot spot in the image, and this is what we use to classify this zone as being detected. And what we've done in our testing is that we can detect sleeping newborn babies that are in rear-facing child seats, because that is one of the advantages of mmWave technology, is that it can actually transmit through certain kinds of materials, such as the car seat, the back of a car, and be able to still detect the life form in the seat. This also helps us be able to have good detection rates, even if the child is covered in thick clothing or a blanket, as well as being able to have low false alarm rates due to things such as the vehicle being shaken, or water bottles or things that are kind of just sliding around in the car. In addition to occupant detection, though, you can see that because of this wider field of view compared to a camera, that you can also detect intruders that are approaching up to the vehicle. In addition to just being able to do a single child detection, we also are able to do multi-zone occupant detection, which similarly to the concept I explained earlier in this image here of the output, you can see that the corresponding positions show higher energy intensity levels where we have 3 adults. And then here we're using a simulated child-based test. It's a baby doll that breathes similar to how we expect a human to breathe. And that's the main thing that we're detecting here in these vehicle occupant applications is the presence of a human causes the energy increase, and that breathing motion is really what we're capturing. Again, as I stated in the beginning of the presentation, you can think of radar sensors as being able to detect motion, very, very fine motion, such as the breathing of a child with a very small displacement of that chest, as well as being able to accurately localize where that motion is compared to other kinds of motion detection capabilities. This is one of the key distinctions with radar is being able to distinctly localize where that motion is coming from, as well as the degree of that motion with velocity information. Using the sensor here, we can see that there are some advantages with this small form factor. It allows you to place it in various different positions within a vehicle in an unobtrusive manner. Here we're doing it in a front mount application, but it can also be embedded in the ceiling roof liner of the vehicle, as well as other positions in the car or application as required. So to dive more into the sensor that was used in that image of the testing results, this is the antenna on package device. So this whole chip includes both the processing capability as well as the antenna being on the device. It's a very small form factor of 15 millimeter by 15 millimeters. The 6843 devices, the 4 means that there's 4 receivers noted here, and then 3 transmitters, giving us a total of 12 virtual antennas. Typically in other millimeter wave devices that are not antenna on package, you have to develop the antenna and produce them, requiring some specific capabilities from your manufacturer. Using the AOP technology, this simplifies the production and testing development process. And with this arrangement of antennas, you have both elevation as well as azimuth detection capabilities, giving us a 3D point cloud with azimuth resolution of 29 degrees and elevation of 29 degrees. I do want to make a distinction for people new to radar technologies is that when we talk about angular resolution, it's a little bit different than what is typically considered for optical technologies. Here, what we mean when we say angular resolution is that if you have 2 objects in a scene and they are both in the same range and Doppler bins, essentially that they're the same distance from you and they're moving at the same speed, they would then you would need 29 degrees of separation to be able to classify them as 2 different objects. Otherwise, they would be considered as 1 object. But typically, with radar, we have really fine velocity resolution. So that's generally, you have very fine range resolution and then even finer velocity resolution. So your range resolution is about 4 centimeters, and then your Doppler resolution is mainly constrained by both your chirp design and the memory constraints. So that can go down to the order of about 1 centimeter per second. And so that distinction, those 2 resolutions is how we're able to separate out fine point clouds even in a tightly packed car, is because of those 2 vectors in which we can distinguish points more so than on the angular resolution. But again, the key thing to note is that this particular antenna arrangement gives you good field of view in both azimuth and elevation, so that we have about when we're mounted in the car, we can have this close to full coverage of the vehicle on the front row and the second row for detections. So going into some more details on the benefit of AOP, this form factor that the antenna on the package is gives us reduced complexity as well as small form factor, not needing to be able to stimulate and design an antenna for a specific application would accelerate the design and production time. Again, with the typical PCB type of antenna, you have to use a specific type of PCB material, which is generally higher cost and requires some specialization in the manufacturer to be able to produce those. So by using an AOP device, you can use a standard FR4 board and as well as have a wider range of options in the supplier that you use. In comparison, also one of the issues that you can sometimes see with PCB-based antennas is some routing losses due to that interface. However, with the antenna being on the package here, we see a reduction in those inefficiencies and enabling us to have higher gain overall, which translates to better range or SNR performance of your radar technology. Some more examples of using the AWR 6843 AOP for child presence detection test. This is some more recent test results we released in the last month. Is again, you can see the sensor here being mounted in the ceiling type application now. So it's overhead instead of before where we were looking at more front facing application. This image here gives an idea of the sensor placement within the vehicle. And then what we can see here is that, again, using that child doll that I was talking about earlier for simulated motion of a child breathing, we tested the positioning of the child in various different positions within the car. And you can see here the point cloud I was talking about, where the sensor is able to detect that motion and generate a point cloud that localizes where that motion is within the vehicle. So that's how we can determine which zone, if here we identify these zones as 1, 2, 3, 4, and 5 within the vehicle, and that we tested them across all 5 zones, and we're able to show that there's detection in both a front-facing and rear-facing application. Again, radar sensor being able to see kind of through in this rear-facing, see through that front part of the child of the car seat that's kind of obstructing the view and still be able to detect that motion. Again, this shows now the same sensor. So the multimodal advantages of being able to that you get with using mmWave sensors, in addition to being able to do something like child presence detection, we're using the exact same software to be able to also run occupant presence detection across the different positions in the vehicle. And here we're showing some test results of our multi-person testing. We have a person in the driver and passenger seat here. And again, the point clouds localize them into those 2 positions for accurate detection of those occupancies, as well as in these diagonal test cases and these backseat tests. So what we're showing here is that this point cloud gives you the ability to distinguish positioning within the vehicle. And then also in addition to within the vehicle, because of that wide field of view that you get with this AOP antenna, you'll also be able to do intruder application type detections. So here it's actually the same sensor, the mounting position hasn't changed at all, is also able to detect when someone is approaching from the outside and potentially like reaching into the vehicle. So you hear in this panel here on the bottom right, you can see that we've defined another zone just outside the car, and when the person is standing outside and reaching into the car, you get point cloud that reflects both of those actions. And compared to previously in this kind of control, when there's no one in the scene, you pretty much don't have any detections here because we're able to ignore just static objects and really look for motion-based movement related to human movement. And that's the same case. This is showing just the approach from the other side of the vehicle. Here's some examples from one of our third-party partners. is a similar type of multimodal sensing, is that same sensor, again, being able to use to be able to detect intruder detection. And this is a similar kind of output, someone approaching from the outside. And then also being able, that same sensor being able to localize 5 occupants in 2 rows and classify these occupants as being an adult or a child. Here, the rendering you can see is a little bit different, but again, there's a point cloud superpositioned over this image to show the kind of detections we get from this sensor. Okay, so to get started for in-cabin sensing 60 gigahertz evaluation, we recommend looking at the AWR 6843 AOP EVM. It gives you 120 by 120 degree field of view with angular resolution of 29 degrees in both directions. In our testing that we've shown in our reference design down here, we've done roof mount to show detection of 4 people across both the front row and the second row, and child presence detection across 2 rows, as well as the footwell, which is the floor beneath or behind the seat. You can reference the software that we put available open source on TI Resource Explorer, as well as the design document that goes into the details of the algorithm, as well as our testing results. A video of the snapshots we showed earlier is available at this bottom link. And again, for anyone who is looking at radar sensors but is not specifically interested in in-cabin sensing applications, the same link will also take you to our general software repository that has other application software such as people detection for HVAC applications, gesture detection for both kind of infotainment as well as general consumer electronics applications and heart rate monitoring. Again, underlying all of these technologies is the same kind of sensor, the 6843 AOP sensor, which enables you to detect motion with a high degree of fidelity as well as localize that motion. Okay, well, thank you for attending.
Great, thank you, Amanda. Thank you, everybody. Just a reminder, the link here shown on the slide will be where you can find the recording of this webinar, as well as a PDF version of the slides. And with that, we just have 2 more webinars to close out the year. Next week's webinar topic will be ultra-low IQ buck boost converters. And then the week after that will be thermistors. And then we will be done for the year and we'll pick back up that first week in January. So thank you, everybody. We will have the presenter as well as a few people on the team stay on the WebEx for a little bit longer. And if you have any questions, please use the chat and we will help answer in real time. Thank you.